Now, there's another way that we can talk about vectors, and this is what we call the algebraic interpretation of vectors. What we can do is put a vector into our xy graph with its initial point at the origin. When we do this, we call it a position vector. So it's positioned so that its tail is right at the origin. But what this means, if we've got it this way, then the end point we can actually list as a point with an x-coordinate and a y-coordinate. When we write a vector this way, then we've got the point that's its end point. Instead of with parentheses, we write it with these kind of brackets. For this, if you've got something with pointy brackets, that means it's a vector. If we're talking about vectors geometrically, they're a line segment with a direction. Algebraically, though, they're basically an ordered pair. The first number in the ordered pair is what we call the horizontal component. And the second coordinate is what we call the vertical component. That's just because that's what they look like on the graph. So for this vector, if we split it into its horizontal component and its vertical component, that gives us a right triangle with the horizontal and the vertical being the two legs of the triangle. When we draw our vectors this way, then the angle between the positive x-axis and our vector is the direction angle. In this picture, the theta right here would be the direction angle for our vector. If we have a vector written in this form and we want to find the magnitude or the length of this line segment, we would get by using the Pythagorean theorem. Our magnitude would just be the square root of a squared plus b squared. This is just like what we did at the beginning of this course where we were using x, y, and r. The r was the square root of x squared plus y squared. The other thing we can find out is our direction angle if we know the a and the b. If we look at this as a right triangle, for our angle theta, the tangent of theta would be b over a. So we can use that if we want to find the angle, then we would do the inverse tangent of b over a, and that would give us that angle. Let's find the magnitude and the direction angle for this vector. This gives the point that is the end point of our vector, or the terminal point of our vector. So if we have 3, -7, there's the point 3, -7. That means our vector is starting at the origin and going to that point. If we want to find the magnitude of this vector, so we're just going to take each of those and square them, and then take the square root. That would give us the square root of 58 for the magnitude of our vector. We could write it in here as the length of this. Then for our direction angle, if we do b over a, that's going to be -7 over 3. So what this is going to give us is the angle from here to here. If we use the inverse tangent on our calculator and put in a negative number here, it's going to give us a negative angle. So this is going to give us -66.8 degrees approximately. So that's the negative angle from here to here. Usually we talk about direction angles as being positive. So then what we want is the angle that's coterminal with this but positive. So we would take this and add 360 degrees. So for our actual direction angle, it would be these two added together, which would be 293.2 degrees. If we have a vector where we know the magnitude and the direction angle, and we want to split it up into the horizontal and vertical components, we can just think of it as being a right triangle and use our trig relationships, but there are also some formulas that we can get from that. So whether you want to do this just by drawing the picture and figuring out the trig relationships, or whether you want to memorize the formulas, that's up to you. So let's look at a few examples of this. In this one, we know the magnitude and the direction angle of our vector, and we're trying to find the horizontal and vertical components so that we can write it in this form. If we draw the picture of this, if the direction angle is 220 degrees, that's going to put us over here. And then we know our magnitude is 14.5, so that's the length of this line segment from here to here. Now what we're trying to do is find the horizontal and the vertical components of this. So this is just like what we did in the beginning of the semester. This would be the same thing as the R, and we're trying to find the X and the Y. So we could do this just using trig relationships and look at this right triangle right here. If we wanted to do that, then we need to know this angle. This was 180 degrees to here, so to get to 220, that would be another 40 degrees. If we wanted to find the X, we'd be using the cosine of 40 degrees, since this would be the adjacent side, and then this would be the hypotenuse. Now, if we do it that way with an angle of 40 degrees, it's going to give us a positive answer for X, but we know that X is negative because we've got the picture. So we're still using this idea. And then we would just be solving this for X. That's going to give us approximately 11.1. So our A that we're trying to find for our horizontal component, our A is going to be negative because this is going to the left. So our A would be approximately negative 11.1. We could do the same thing to find the B. In this picture, we've got the Y. Y over R is sine of theta. We know the R is 14.5. We've got our angle of 40 degrees. So we would solve for Y by multiplying 14.5 times sine of 40 degrees. That would give us 9.3. Again, for this one, because our point is down here, our component B is actually going to be negative. That means that B would actually be negative 9.3. And we could also do this by using these two formulas. In that case, we'd be using the direction angle that we were given, and that way we wouldn't have to worry about the signs. If we did it that way, we'd have for A, the magnitude of U was 14.5, and then we'd have the cosine of 220 degrees. This is going to be negative, so when we multiply that out on the calculator, that's going to give us negative 11.1. For the B, we would have the magnitude times the sine of 220 degrees. This is also going to be negative, so that's going to give us the negative 9.3. So either way, we've got these two values for A and B, so then we could write our vector U in that form, with the A, the horizontal component, and the B, the vertical component. Here's another example. This time we have a magnitude of 4 and a direction angle of 135. If we draw the picture, 135 degrees is going to be over here. If our magnitude is 4, that means that the distance from 0, 0 to the end point of this is 4 units. So that would be our R if we were thinking in terms of X, Y, and R. What this also tells us is that our horizontal component is going to be negative because we're over to the left, but our vertical component is going to be positive. So the A in this is going to be negative, the B is going to be positive. So here let's just use our formulas. For the A, we're going to take the magnitude times the cosine of our direction angle. That's 4 times the cosine of 135. Turns out 135 degrees is one of our special angles. The cosine of that is negative square root of 2 over 2. And that would simplify just to negative 2 times the square root of 2. If we were getting a decimal approximation, that would be approximately negative 2.8. For the vertical component, we would take 4 times the sine of 135 degrees. This would be 4 times the positive square root of 2 over 2, which would simplify to 2 times the square root of 2. The decimal approximation would be approximately 2.8. So our vector v, if we wrote the exact values, here would be our horizontal component and our vertical component. Okay, then last one, vector w has a magnitude of 10 and a direction angle of 340 degrees. 340 degrees would be over here in the fourth quadrant. So we already know that our A, our horizontal component, is going to be positive, and B, our vertical component, is going to be negative. So for A, we're going to take 10 times the cosine of 340 degrees. That's going to give us approximately 9.4. For B, we're taking 10 times the sine of 340 degrees. That's going to give us an approximate answer of negative 3.4. To write the vector with the horizontal and vertical components, it would be 9.4 and negative 3.4. Now here's another example where we're trying to find some information about the resultant vector of two vectors. And this time we're going to draw this in the plane. So we can use the horizontal and vertical components in this to help us. So in this time it doesn't give us the direction angles of these two forces, it just tells us the angle between the two. So I'm going to draw this so that our first vector is actually on the horizontal, so it's on the positive x-axis. If the force is 32, that means that's the magnitude of our vector. So our first vector is going to start from the origin and go here, and we know that the length of this line segment would be 32. So for this vector, we already know the horizontal and vertical components. The horizontal component would be 32 and the vertical component would be 0. For the second vector, we know the angle between the two is 76 degrees. So we can just draw this one 76 degrees away from the first one. And this one has a magnitude of 48 newtons, so we want to make it longer than the first one was. So this distance is 48, and then this angle is 76 degrees. And what we're trying to find is the resultant vector. So since we have it drawn this way, we can do a parallelogram. And then our resultant vector is the diagonal of the parallelogram. So our resultant force is this vector right here. We could do this one by using the law of cosines, but another way we could do this, since we already have the horizontal and vertical components of this vector, we could find the horizontal and vertical components of this vector and then just add those together to get the horizontal and vertical components of our resultant. So let's try it that way. For the second vector, we've got a direction angle of 76 degrees and a magnitude of 48 degrees. So for that one, our A would be 48 times the cosine of 76 degrees. Our B would be 48 times the sine of 76 degrees. That's approximately 46.6. So that vector written in component form is going to be like that. Now our resultant vector is the two vectors added together. To get that, we just have to add the components together. So if we're adding our two vectors, we're going to take these two and add them. So we're adding first coordinates to first coordinates. 32 plus 11.6 would be 43.6. And then here we're adding 0 and 46.6. So this is our resultant vector. Now what we're really trying to find is the magnitude of the resultant force. So now that we've got our two components, we can use that formula that said that the magnitude is the square root of a squared plus b squared. So we're just going to work this out. This ends up being approximately 63.8. So the magnitude of our resultant force would be 63.8. The units are going to be the same as they were for the other two forces, so this is going to be newtons. Now what we just did was operations with vectors that were already split into their horizontal and vertical components. We can do several different operations with our vectors written this way, so we can add or subtract, just like what we just did. Here to add or subtract, we're just going to add or subtract the components. If we want to multiply a vector by a scalar, then all we're really doing is distributing the scalar to each of the two components. So here we're just distributing the scalar. And for this, if we're looking at the opposite of a vector, again, we're just distributing the -1. Or we could think of this as distributing the negative sign. So there's nothing very complicated about any of these if you already have them written in component form. Let's do some examples of this. If we've got these two vectors written in component form, if we want to find u plus v, which would be the resultant vector, we're just going to take our first components, our horizontal components, and combine them. 6 plus a -14 would give us a -8. And then our vertical components, we'd add those, and that would give us a +5. So there's our u plus v vector. This one we're just taking -1/2 times our vector v. We're just multiplying the -1/2 times each of the two components. That would give us a +7 and a -4. And then here we're taking 5 times the u vector plus 2 times the v vector. So here I'm going to distribute the 5 to both of these components. Here I'm going to distribute the 2 to both of these components. And then I'm going to add my corresponding components together. So 30 plus -28 would give me a +2. -15 plus 16 would give me a +1.